It can also work overnight, then methylation changes and epigenetic changes you can see. And not shown, but in 24 hours or 2 days you will see metabolomic changes. But it is for very long time, then only genetic changes come. That also emphasizes if we can detect those changes early, then we can do something about that disease. And here we have like in different cancers the way about genetic information we know, similarly now about epigenetics that information is covered. In fact, certain genes have been identified which regulate methylation, but in that methylation these mutations have been recorded. So they are going in some cases. Peter Jones and Andrew Feinberg. Peter Jones is at Michigan and Andrew Feinberg in Johns Hopkins. They were the pioneers who started thinking about epigenetic regulation, in which they saw that when active transcription is there, then histone is acetylated. At inactivation, it starts getting deacetylation, and at complete silencing, it gets methylated by DNA methylate transferase. And if you see chromatin at top, the chromatin it is called relaxed or quite apart, and yellow color shows acetylation, but gradually this red color methylation starts, and many other transcription factors, other gene regulatory factors come, and these chromatin get so compact that transcription stops, and that's how epigenetic regulation works. And when methylation is also done, then one strand is methylated at one time, another time, and S-adenosine methylate, that is called S-adenosine 16. So whenever you do such kind of experiments, so both strands should sequence. At different stages of cancer development, these are the mutations, but in epigenetic changes, overall, initially, because of line and sign sequences which cover about 90% of the genome, they are already methylated, their CPG sequence. So gradually with disease development or lifelong, global hypomethylation you will see, but for specific gene, chromatin gets hypermethylated. And histone modification, initially they are not there, but they increase in cancer. So this is one paper where they have measured that line 1 methylation status in prostate cancer, how it increases. So very systematically that was done to show line 1. These are also called jumping genes. So initially they just knew that they will go somewhere, but because of epigenetic regulation, this happens. Methylation also can happen either abnormal increase or decrease or no change in like in tumor suppressor genes, either methylation of both alleles or one allele and DNA imprinting of one gene and another methylated. In abnormal decrease, it happens in proto-oncogenes or latent viral activation. If you remember in early 90s, when gene therapy just came, then retroviral vectors were used to introduce healthy gene in the by recombinant technology. Since retroviruses were used so many times, their promoter, which is called LTRO, so those were hypermethylated and inactivated. That's why those vectors did not work and recombinant DNA also did not work. But at the time, methylation and other things were not very well characterized. Now we know that. So now such vectors are created where that problem does not come. Wherever no change is there, then either chemically induced mutations or poor repair or deamination. So these are different combinations of possibilities which can arise due to DNA methylation. vaccine pictures. They can be used. In epidemiology or epigenetics, by two ways. Either you do profiling, you know which group of microRNA are increasing or decreasing. Based on that, you can tell whether some diseases, cancer is developing or not, or response to therapy, or those genes which are coding for microRNA. If there is any polymorphism, that also you can follow. MicroRNA, they either increase or decrease, so for in different diseases that people have followed. So for lung cancer, microRNAs will be different than liver cancer. And nowadays another concept is also coming about exosomes. So somehow among all RNAs, microRNA are the one which get concentrated in exosomes. So those that can be collected first of all non-invasively, and microRNA from that can be characterized and can be used for cleaning purposes. So this is the one we wrote before some time, extracellular vesicles or exosome, and how we can utilize that. So a lot of research is going on. Those exosomes contain not only microRNA, sometimes DNA is also there, or protein or metabolites. So how they can be utilized. Regarding histone, as I mentioned, 4 kinds of subunits are there, and these are the tails of these histones which are modified, whether at in or other position, and those modifications are shown which in different cancers have been reported. When we initiated roadmap epigenomics at NIH, then what we did, we gave contract to 2 companies to raise monoclonal antibodies against these modified moieties. So that can be used for screening purposes, and that was distributed to different investigators. And in those histone modifications, some will be for writing the instructions, some will be for removing. So all those also have been characterized, and along with histone, other proteins to be characterized. And now technology exists, like it is called chip on chip. So by immunoprecipitation and other techniques, you can identify first by breaking chromatin and then precipitation that which chromatin or modifications are there, and at different times you can identify and sequence in which sequence which histone modifications are important. And cancer-related histone modifications, most of them are only 9 to 11. So anybody starts any project for screening purposes or other purposes, then we recommend that those should be used. And here they are shown like S3 protein, lysine 4, or lysine 9 or 27, where this is where they are acting, whether they are, how they are modified. So all those have been characterized. And these are used for diagnostic purposes also, histone modifications, and to combine and promote the field. Time to time I have edited different books either on cancer epigenetics or cancer epidemiology for post-receptor factors or modifiable factors of cancer biomarkers. This year was on progresses and challenges in precision medicine. As you know, that every individual is different, so how we can utilize this information if doctor follows a patient and takes samples again and again. I was interviewed one time by Nature to know why epigenetics is important compared to genetics. Then I emphasized that if you have mutation or certain changes in gene, you cannot go back, just you can use that to tell what disease will develop what. But these epigenetic changes, methylation and histone, you can reverse. So epigenetics has slight edge over genetics. And then next year again I was interviewed by the same journal. Then by that time certain drugs were introduced or identified, whether they were methylating or histone modified. They can do histone modifications, so were also identified. And different pharmaceutical companies, they started working on those drugs because of those epigenetic indicators. In methylation projects, different kinds you have to keep in mind as different kind of control to reduce false negative or false positive, like total methylation content or methylation level at a specific stage, or file of methylation of 5 specific genes or a number of genes, or pattern or epigene. But if all these controls are, then methylation profiling will be very accurate. Steve Bellin, who is also in Johns Hopkins, he works on epigenomics or translational epigenomics mode, and they have characterized more non-histone proteins as well as different transcription factors and other factors and histone. They are sequenced when they are released, and they do that kind of work. Suppose in H3 histone, K27 is time, then the gene will be involved in differentiation. Or if next amino acid, in this case S3K9 methylation is serine, then change will be permanent. So those kinds of basic research is also going on. Now at different stages of development of cancer, like progressive detection, then diagnosis or therapeutic time, in these stages, different exfoliated cells come. So if these samples are collected, then many markers can be characterized from that. For different types of cancers, investigators have done in different setup or institute, group of genes have been identified which in these cancers is hypermethylated. Similarly, other kinds of proteins are there in which changes or other changes are there, characterized very well. Against those proteins or methylation changes, in different drugs are being developed. These are the ones for methylation changes in different trials or histone changes. In that, some of the promising results are also coming. Some adverse reaction like dehydration, diarrhea, nausea, vomiting, those you see. But still against fat transferase or DNFTs, against that, these are those drugs which are in pipeline. Whether it is Johnson & Johnson's or SmithKline Beecham, or all of them have programs against these epigenetic drugs. If you get a chance to go to ASCO, American Society of Clinical Oncology, the latest results are presented there. And these inhibitors belong to different classes: short chain fatty acids or aliphatic compounds or cyclic tetrapeptides, benzamide. And same way, stone deacetylases are also being characterized, like different forms are there. So against the forms also, those inhibitors are being developed. So these inhibitors provide a novel class of anti-cancer drugs, and sometimes they work as radiosensitizers, like regular treating agents. If you put, then many patients will not respond. But if you treat with epigenetic inhibitor first, example, one of this is methylation drug, valproic acid, in those patients more than 50 where no other drug was approved. So this combination was given by pyrosequencing. This methylation was done, and chip-on-chip analysis histone was done on day 148, and they started responding. Similarly, in other examples, combination of 5-azacitidine for demethylation, valproic acid for post-translational myeloid leukemia and myelodysplastic syndrome that was used whenever at NCI we have several clinical trials. There are stroke inhibitors, whether these are solid tumors or leukemia or lymphoma, breast cancer, glioblastoma. These are of lung cancer, along with proteomic marker, these epigenetic, and even in sputum you can do that test, and Steve Belansky has done this kind of work. As best as exposure is just by methylation profiling, those groups can be identified. In esophageal cancer, when it is the early stage, so methylation pattern in 20 genes or so if you follow, then some early stages, some are the later stages. So longitudinally follow the patient, you can tell that high risk of developing this cancer, and that methylation profiling can be correlated to survival also. Survive. Many times people ask for clinical trials, why we collect patient history, exposure history. Because if somebody is alcoholic, they have a limitation, long-standing diabetes, and for many, currently we don't have early detection markers, but along with those which are 50, 60, and 80, they get hypermethylated. Otherwise, kidney cancer, in 1 or 2 years, by it's too late. For breast cancer, lung cancer, colon cancer, and some other cancer, it takes 15, 20 years, but these are considered better. Cancer treatment can also be followed by based on methylation profiling. Now comes those infectious agents. Many infections, HPV, SV40, HCV, EBV, pylori, they have been associated with many other cancers. In fact, if we see all cancers, then 15% of total cancers are involved. And in that, latency associated nuclear antigen or Epstein-Barr virus, they are the main genes which are involved. Recently, for papillomatosis, which is for cervical papillomatosis, EBV, if that comes to cervical cancer, those methylation profiling has been done. Why we are interested in these kinds of research? Just by pathological examination or histology, you cannot tell that a person is cancerous or not, but if we do profiling, then we know that the person is at high risk. Here, like in HPV, early genes or C6, C7 or late genes are there. Whatever genes, when it is methylated and what was the extent of methylation at different stages, those have been characterized completely. And to promote this area, we have put on HIV, AIDS or other viral methylation also. That area we are promoting. Of liver cancer, that hepatitis C or C, those are being characterized. And in hepatocellular carcinoma, Asian and Japanese population is there. One gene was observed where hypermutation was observed in Japanese population. Sometimes some changes are very much population based. Some are very common, like for hepatocellular carcinoma. This gene generally gets methylation. In immune system also, T cell or B cell, GD-Z development, but then there is different function. Epigenetic has been characterized very well. And T-cell methyltransferase in cancer and other disease, those data have been characterized. Now in prostate cancer, mostly PSA is the one which was used to screening you, but when level is less than 4 nanogram per ml, then clinician does not know whether they should wait or they should treat, because prostate cancer is such a takes long time to develop, it has a chemotherapy radiation. Environment and lifestyle and diet and exposure, they play a major role. So if you change that, then you can prevent cancer. In fact, so that kind of research was done, and in liver cancer one model was developed where no carcinogen was added, just supplied, and such kind of situation was developed. It was very similar to liver cancer. And their biological components, those were characterized. For example, in turmeric, cinnamon, or apple, or citrus, or coffee, broccoli, garlic, etc. So some food have demethylating properties. Some have only histone modification, anti-histone modification properties. Some have. Institute of Alternative Medicine, where they are trying to utilize that natural food, how they can do and how much epigenetic mechanism. I also wrote one article on nutrition and to cover that area. Now comes what NIH has promoted this area. When Dr. Zahroni was director of NIH, that time he initiated one program that about 1.5% of budget, if all institutes contribute, then that can be utilized to understand such biology which is good, but it will be very helpful. So in first round, microbiome and epigenetics, these programs was promoted because epigenetics disorder that was observed. But it was not known the way we have in genome. From healthy people also we have sequence. In proteomics we have proteomic profiling. For methylation profiling and histone and microRNA and others we did not have. So this epigenomic roadmap program was, idea was of that roadmap program that 5 to 10 major projects can be started which are of high risk, but for them they can contribute a lot in translation or transformative biology. So after that, other director came and Francis Collins came, so he changed its name. And as an example, you can see that in 2015 and 16 also, same amount, about $500 million were spent. And I have been involved in 3 major programs from the start: epigenomics roadmap program, and then this molecular transducers of physical activity. So in that we are doing some part-time profiling is there, of increasing the capacity to do that kind of analysis. So that is done, and programs which are going on, like single cell analysis, they are about global health, science and behavior, genomic tumor expression, genomic roadmap you can imagine, and these are all congressionally mandated programs. So first to this program, then only it will be distributed to others. So in 2008,